Good morning, everybody. Welcome to today's webinar presentation. I'm just looking at the log-on screen here. Looks like some additional people are still signing on, so we're going to give it another minute or two before we start today's presentation. Okay, we're going to begin today's presentation for the anaerobic operator webinar series. Today's presentation is one of my favorite topics that we've done so far. It's called All About Sludge. My name is TJ Willits, and I'll be the moderator for today's presentation. Some housekeeping items to discuss before we hop into our technical portion of our presentation. There are two options for audio. The one would be listening through your computer or your headphones, and the other one is a dial-in using your phone. So choose one of those options to hear today's audio for the presentation. Also, this webinar is being recorded, so at the end of the webinar, in about a day or so, you'll be sent out a link to watch the rebroadcast of this presentation for your viewing pleasure. Also, there's a questions panel on the right side of your screen likely. If you have questions throughout the presentation, feel free to go and enter them in that question box, because at the end we reserve some time for us to ask our technologists some of the questions that you may have come up while you are watching the presentation. Additionally, at the end of the webinar, you'll receive a link to a survey or a request to take a survey. Please take the few moments it takes to do that. It really helps us to shape the content and improve these webinars continuously to make sure that everyone who attends them is benefiting from them. More importantly, and we'll remind you at the end of the broadcast, put things in there that you want to hear about for content. We're always looking for new ideas or new topics from our customer base that have the technologies that we produce. We want to make sure that you're being provided the technical information and the continuing education to be the best operator that you could possibly be. Also, many people want some participation certificates for continuing education. If you do want one, in the surveys how you request one. And also, if there's multiple people watching from one of the computers that needs a certificate, a continuing education certificate to prove that they were here, please enter their names in the survey as well, so we can make sure that everyone receives those certificates. And we normally get those out within a week or so of the webinar broadcast via email. With us today is Jill Jordan, our Senior Process Specialist here at Veolia Water Technologies. She's one of the most experienced people in the country for high-rate anaerobic reactors. We've talked a lot about her in previous webinars, and I'll save the time of going through her resume. And at this time, I'd like to pass it over to Jill. Jill, are you with us today?
Yeah, I am here, TJ. Can everybody hear me? Can you hear me, TJ?
Yep.
Okay. Thanks, everybody. I'm glad to see everybody's here today. And it's an apt subject for me because when I first started doing this, one of the names that one of the operators gave me was Sister Sludge. So that has followed me for 30 years now. And today we're going to talk about anaerobic sludge. So we're going to talk about what is anaerobic sludge, the different forms it takes, and what you can do with it. And I love this picture with somebody's hand picking up these nice granules. Next. So, first of all, what is sludge? It can also be called biomass. It can also be called biosolids. It can be called the guys, the stuff, whatever. And it's a mixture of various microorganisms, mostly bacteria, archaea, fungi, some nematodes. And what develops is a conglomerate of the above that's based on the conditions that it lives in and what it's trying to treat, because we're using these microorganisms to treat the waste in some way. That's either wastewater or waste solids. And we're going to try and reduce the amount of waste in the wastewater system. So like reduce the amount of COD, or in a solids digester, you're going to want to reduce the amount of solids. You're actually going to eat the solids, convert them to something soluble, and then convert that to biogas. Now, these bacteria come in a number of bacteria and fungi and archaea. Mixture conglomerate can operate sometimes in aerobic modes, sometimes anoxic modes, or anaerobic. Again, today we're going to talk mostly about the anaerobic, which means without oxygen. Okay? So, the sludge works to reduce biodegradable compounds in wastewater treatment streams and to break down volatile solids in solids digester. And the byproduct of this breakdown is biogas. There's a mixture of CO2 and methane and some other compounds. And what can those other compounds be? Well, they can be new sludge, or they could be something like hydrogen sulfide, because there's also bacteria, anaerobic bacteria in this conglomerate that will reduce sulfate compounds into hydrogen sulfide, which is that yucky rotten egg smell that everybody complains about with anaerobic digesters. Next. So there's two main types of organisms that make up anaerobic biomass. So it's sort of like a two-step process. And the first step is done by the acid-forming bacteria. And the second step is done by methane-forming archaea. And archaea, don't get confused, they're basically do the same thing that bacteria do. It's just that since DNA testing has been done on them, they found out that they have a different evolutionary background than bacteria does, so they had to give them a different name. But they do basically the same thing that bacteria do. Okay, so don't get confused with that. We have a little picture. Go back, please. Thanks, TJ. The acid-forming bacteria, you can see at the top, on the top right there, there's a picture of some lactobacillus, which is a type of acid-forming bacteria. And on the bottom is a picture of some methanotrix bacteria, which obviously, from the name implies, it's some of the methane-forming bacteria. And I wanted to talk about this a little bit is because look at the shape of the lactobacillus. It's what we call rod-shaped, and most acid-forming bacteria do take that form of rods. And the methane formers, notice it's longer, so it's more filamentous type. So, and that's an important thing to remember when we talk a few slides down. Okay, so let's talk about the acid formers first. They do, again, the first step in this anaerobic digestion, and they're responsible for three steps, really. They're responsible for hydrolysis, which break down large organic molecules into smaller substrates like a starch into a sugar. A starch can be insoluble, can be floating around, and the first thing that these bacteria would do is to break that down into a smaller molecule, which would then be solubilized in the water. Or think of that hydrolysis in a solids digester would start to break down large pieces of biodegradable material. They start to break down the leaves. They start to break down the pieces of meat. They start to break down starches or pieces of rice or pieces of food. Anything like that, any biodegradable solid. Hydrolysis is starting to break those down into smaller molecules that can be dissolved in water. Now, once you have those slightly smaller molecules that are dissolved in water, you're going to do acidification. In the acidification step, you're going to take those sugars and starches and other carbohydrates, and you're going to convert them into volatile fatty acids. And if you remember from our previous webinars, these fatty acids are acetic, propionic, and butyric acids. So they're very common acids. Remember that acetic acid is just vinegar. Okay, so we now have in this process, we have now all soluble products that have been broken down into these fatty acids. And the final step is called acetogenesis, which converts all those acids into either hydrogen and carbon dioxide or acetate. And we're way down at the bottom On the right-hand side there, you can sort of follow what we just talked about, and you have, notice at the end, we have now 2 squares of acetate and 1 of hydrogen and carbon dioxide. So we're at that point, acetogenesis gets you down to that point in the breakdown of a complex molecule. Now, the acid formers are also fermentative bacteria. So that means there's acid, there's H2 producing acetogens and H2 reducing acetogens that are going to be part of that colony in there. Okay. Next. Also, an important thing to remember is that acid formers are facultative. And what does facultative mean? Facultative means that they will work with or without air. So they're not strict anaerobes and they're not strict aerobes. They'll survive in either condition. And they also survive in a really wide pH range. They work in a pH range of 3 to 8 and a temperature range of like 35 to 104 Fahrenheit, and they reproduce every few minutes. So they're able to make a lot of acid really fast, especially if the temperature's about body temperature. Okay, now, the acid formers did a lot of work, but up to that point, they haven't reduced the COD in any way, which is really what we're trying to do with this sludge. The sludge is there so that it can reduce COD or solids or whatever. So we need the methane formers to do that last step, and it's that last step that finally reduces the COD. Now, the methane formers are strict anaerobes, and there's 2 types. There's acetoclastic methogens, which will take the acetic acid. Remember, see the 2 blocks there on the bottom right there, two squares of acetate, and they're going to convert, the methane formers are going to convert that acetate into methane and carbon dioxide. Then you see there's 1 square that has hydrogen and carbon dioxide in it, and the CO2 reducing methogens are going to take that hydrogen and CO2 and convert it to methane and some water. So most of the biogas that's produced, most of the methane that's produced in this process comes from the reduction of acetic acid or acetate into methane and carbon dioxide. And it's when you make this biogas, that's when you've cleaned your wastewater and you've reduced your solids as much as possible. So again, the methane formers are archaea that produce methane as part of their metabolic cycle. Now, they live in living conditions that are way different than the acid formers. The methane formers work best in a pH range of 6.8 to 7.4, and you'll notice on the upper right-hand corner of the slide, there's a chart that shows the activity of methanogens with respect to pH, and you can see you get 100% activity at a pH of about 7.2. So that's the best place to keep these guys working and working best. If your reactor pH would go down to 6.5, you can see that the activity of the methane formers would be reduced to like 30%. And if I went up to a pH of 8, the activity would go to like 50%. So if you're trying to make your reactor work at pH range outside of about neutral, you're going to need a lot more sludge to make up for the fact that your pH is not, to make up for the fact that the methane formers cannot work as well with those pHs. And similarly, we have another chart at the lower right-hand corner that shows the activity of methanogens with respect to temperature. And you notice that they're most active at body temperature. 98.6 is perfect for them, so it's like 37 degrees C, but they work best between 90 and 100 F. If I go down to 25 C, which is about 75, again, I go down to 50% activity. Notice that on the right-hand side of that curve, the activity drops much more rapidly with high temperature. So they're much more susceptible to problems at higher temperature than at lower temperatures. And remember that, again, if you will try to operate your reactor at a lower temperature, you're going to need more bacteria because the methanogens activity has been reduced. Now, the final thing with these methane formers is that they only reproduce in the time of days. So if you remember back from the acid formers, they live in any pH, a wide temperature range, and they reproduce every few minutes to every few hours, the acid formers can way outproduce the methane formers. But you need both of them to work together in unison to make the process work. So let's talk a little bit about biomass activity. When you have an anaerobic reactor, you're usually doing normal testing, and you can actually calculate the activity of your biomass on a daily basis if you want. And that's just the amount of COD reduced per kilogram of volatile suspended solids in your anaerobic digester every day. Okay? Now, that will enable you to estimate the possible operating F to M that you want to work at. And then F to M is the kilograms of COD that you put in every day per kilogram of VSS per day. Okay? So that F to M needs to be slightly less than the activity. If your activity is only 0.5 kilograms of COD reduced per kilogram of VSS per day, you can't put 1 kilogram of COD in per kilogram of VSS because the bacteria won't be able to eat it. And in that situation, it's likely that the acid formers will continue to work, but the methane formers won't be able to keep up, and you'll get your system in a point where it's not stable, and your volatile fatty acids and your effluent will be very high, which we all know is a bad thing. So you need to make adjustments to your system as your operating systems can change because the activity can change based on the conditions that your reactor is in. So if your pH drops, your F to M that you need to feed at has to be less because you know that activity is going to drop. Okay. On the right is just an example of an activity test that we're able to do in our lab. So we can actually benchmark the activity of your sludge. If you send it to us, we can test it, and the results will be presented to you in a table form like you see on the right. So this picture on the right shows our respirometer, and one of our nice interns that we had here a couple of years back using our respirometer material to do an activity test. We can test about 4 samples at a time. We have 8 cells of 500 milliliters. We've put some of your sludge in those cells, and we feed it a standard mixture of fatty acid solution, a mixture of acetic, propionic, and butyric acids, and we measure the gas production over time. And that gas production over time and the COD reduction over time tells us the activity of your sludge. And it's good to get a good background biomass activity so that you know the potential of your biomass. This test will tell you the potential that your biomass has at any given time. And we consider a good activity in this test to be at least 0.45 kilograms of COD reduced per kilogram of VSS per day. And you can see in the bottom left-hand corner here of the slide is a chart that we made up for a customer that was having their biomass activity tested on a regular basis. And you can see it varies all over the place. It goes from like 0.61 all the way down to 0.13. At one point, I thought this had to do with a temperature change over the seasons because this particular customer had no temperature control and their reactor ran at very low temperatures in the winter. But as you can see, their maximum activity was actually in the months of January and February. So that didn't go. So I don't know why that one in April of 2016 was only 0.13, but it wasn't a very good activity. But I guess it's a good example of showing how the activity of the biomass can change with time depending on the operating conditions of the digester that the biomass comes from. So, what form does anaerobic biomass take, anaerobic sludge? It can be either in a floccular form or in a granular form. You see some nice pictures there of the granules on the right and floc on the left. The floc-forming bacteria is just those acid-forming and methane-forming bacteria free-floating in the substrate that they're in. And they're typically found in anaerobic lagoons, and CSTR type digesters. CSTR, again, is continuously stirred type tank reactors. And the lagoons and CSTRs are typically lower rate wastewater and solids digesters. They're digesters with high hydraulic retention times. So it's usually a hydraulic retention time well over 3 days, or a solids retention time if you're digesting solids over 3 days. The typical concentration of the biomass in a CSTR or a lagoon is typically about 1.5 to 2.5%. That's 15,000 to 25,000 milligrams of TSS per liter. And the other thing to remember is that this floc form can often be hard to separate out of your wastewater. So if you're treating wastewater with a floc type digester, it can be hard to separate out. You don't want to, if you don't want a lot of solids in your effluent, you would have to add some polymer, some flocculent coagulant, so that it would congeal some in a better form, which is actually what's shown in this picture here. That's had some flocculant and coagulant mixed with it, so it's held together, so it does get some separation. So, granular sludge. You've seen a lot of pictures already of granular sludge, and this is typically the type of bacteria that we deal with. Most of our systems are deal with granular sludge. And why do granules even form? As many different people that are in this business, that's how many different ideas there are, to be honest with you. But I think we all agree on there's several points that everybody agrees on, that it's extracellular polysaccharides that have an effect, which is really sticky stuff that the bacteria make. There's the effect of some calcium. Most sludge is negatively charged and calcium is positively charged, and that opposites attract type deal is what calcium provides. There's also spaghetti theory and mechanical forces. And if you look at the picture in the upper right-hand corner, you'll see what it's sort of like the spaghetti theory. You see the mixture of filaments and rods and some cocky bacteria. And remember that the methane formers are filaments mostly, and the acid formers are rods. So when they get close to each other, they might, the methane formers may loop around the acid formers, and if there's enough polysaccharides, they could stick together. I also think, I'm a big believer in mechanical forces also have a lot to do with it. There's something called collision coalescence, and if you notice in the picture in the lower right-hand corner, that is a cut granule with a nice smoothly cut, and you can see that there's layers there. It's sort of looks like a hailstone, and I think that you also get some of these granules form like a hailstone because they are moving in a circular motion around these high rate systems that they're found in. Next. So let's take another look at some close-up pictures here. In picture number 1, it's a broken granule in the center there. It's just been pulled apart, and if you go in a little closer microscopically to number 2, you can see that the broken granule sort of looks like, to me it looks like a hunk of bread with some fibers in it. And in fact, if you go in a little closer, it is quite fibrous looking, and that fibrous looking look comes from what I think comes from the methane formers wrapped around some of these acid forming rods. And in fact, if you go in even closer, you can see that in picture number 4, which shows a lot of rods and some longer filaments entwined around them. I love this picture. It shows one of the big characteristics that's really important for this granular sludge and why it's so important, the granules are so important, and that is that they settle really fast. And these granules are usually found in these high rate anaerobic reactors like UASB and EGSB reactors. UASB, again, is upflow anaerobic sludge bed, and EGSB is expanded granular sludge bed reactors. And these reactors typically have hydraulic retention times of less than 48 hours. So you get another parameter that has to be looked that has to be considered when you're designing a reactor. You have to know that if you want granular sludge, that your hydraulic retention time of the influent in your reactor is going to have to be less than 48 hours. If it's greater than that, it's likely that you're not going to form granules. You'll only have flock. But one of the big things, if you notice in this picture, is even though this Erlenmeyer flask is being stirred with granules, when the stirring stops, look how fast the sludge settles. And this is even slow motion. Look, it's stopped, and you can see how fast it's settled in the bottom. And that's important because it keeps the sludge in the reactors, and it separates easily, so you get your clean water off much more easily. Next. So the advantage of granular sludge is that I can get a lot higher solids concentration in the sludge bed. The solids concentration in the sludge bed of a granular sludge bed is typically 5% up to 12%. So you can get 50,000 to 120,000 milligrams of TSS per liter in a high rate system with granular sludge. It also means that there's minimal diffusion distance between the acid formers and methane formers. In the flocs scenario, the acid former may not be right next to the methane former, so it can make some acid, and then the methane former has to oh, here it is. I have to sort of get over there somehow to get over and get it before it can be reduced. But in the granules, they're right next to each other. So as soon as the acid formers finish and make all of that acetic acid, the methane former is right there to eat it up. So it's a much more efficient process that way. It's a heterogeneous mix, some symbiotic population of microorganisms in the granule. Also, we get a low sludge growth rates, which means that you have a lot less to dispose of. And again, the high settling velocities allow for retention and easy clarification. Very, very important in these high rate systems. Okay, so we have sludge. We know what it's made of. We know it can take several different forms. What are you going to do with it? I mean, there's always seems to be some excess sludge. So what are you going to do with it? The amazing thing about anaerobic sludge is that it's stable and it doesn't need to be fed. And there's a market for granular sludge, and you can ship it a long way without it losing its activity. So they're all good things that you can consider when you want to do something with anaerobic sludge. So stability means that it's easy to dispose of. In industrial applications like the food and beverage industry, which I think most of you guys are in, you're only treating processed wastewater. So there's no sanitary wastewater in the system. So the solids are pretty easy to get permits to land app or landfill. And because it's the granular sludge is easy to dewater, you usually get them into a landfill too. And each state has its own regulations on what the conditions and parameters have to be able to land app and or landfill. So that's something you have to check within your state of what their rules and regulations are. Now, you don't need to feed this sludge, and it won't lose activity. In fact, if you have to shut your reactor down, it's best to let it cool down because, again, that activity goes down. It's not trying to eat anything, and it won't eat itself. It won't try to eat other bacteria that's in there. In fact, the high rate process was developed in the Netherlands for the sugar beet industry, where they generate wastewater only about 3 to 4 months a year, and then the reactors go dormant and then for 8 or 9 months, and then they can be started up again once the sugar beets are being started. The sugar beet harvest starts. So it's really, really good for facilities that only operate a part of the year or even just 5 days a week, because on those other 2 days, you don't have to worry about feeding them or, trying to keep them alive. They're just going to be there ready and waiting to eat when they get fed again. Shipped over long distances, I'll say. When we made when Biothane Veolia made the first high-rate anaerobic system in the United States, there was no granular sludge in the United States because there were no high-rate reactors. And we actually had to ship in granular biomass from Europe in ISO tankers. And we can still ship to this day sludge in ISO tankers For instance, we built a facility in the Caribbean, and there's no high rate systems in the Caribbean, so we had to put sludge in ISO tankers and have it shipped by sea down to the Caribbean. Very, very good way to do it. Today, in the United States, there's plenty of high rate anaerobic systems, and the transportation between point A and point B is typically done in 5,000-gallon tanker trucks or even septic trucks. Or if there's rail sidings, you can even put it in a 20,000-gallon rail car. The thing you have to remember, though, when you're transferring sludge from tank A to tank B is that, especially if you're transporting granular sludge, you don't want to break it up. You want to keep its granular form. So you don't want to expose it to a lot of high shear forces. Therefore, you can only use positive displacement pumps when transferring granular sludge. And the two types that we typically use are mono pumps or positive displacement, double diaphragm positive displacement pumps. Both of them work equally well. I personally prefer the double diaphragms. They seem to work the best and can offload trucks and tank cars the fastest. Now, when you're selling sludge, you can remember we said there is a market for sludge. If you have excess sludge, you can sell it, and the seller sets the price. And my recommendation is you set the price based on what you would be willing to pay if you needed sludge. Okay, and as a seller, you need to supply an SDS for the biomass, because nobody will transport it without the SDS, and the generator has to provide the SDS. When selling sludge, the transportation cost for the buyer is really the biggest cost. So Veolia keeps track of who has sludge and who doesn't, and we'll try to find a home for it. Or if somebody needs it, we'll try to find some for them. And we will always, because the transportation cost is always the most expensive part of the transaction, we will try to find sludge as close as possible to your location. Can't always promise that, but we try our best to do that so that we can keep the cost down for you. When you're transferring sludge from the reactor to another tank, or from any tank to another tank, it's best to try and keep the sludge moving. So if you're transferring from the reactor, you want to keep it fed so that you're making biogas. That keeps it stirred up. You have to remember that granular sludge settles and thickens rapidly, and it has an angle of repose of like 45 degrees. So you can test this for yourself with your granular sludge. If you put it in a beaker and decant off a good bit of the water and tilt it, the beaker over at 45 degrees, and then put it back flat, it should hold that, the sludge should hold that angle of 45 degrees. It also tends to rat hole. So if you're not making gas, if you're taking it out of a digester and it's not making gas, it'll rat hole, which means that you're going to you'll start pulling some sludge, and then it'll just pull water, and the sludge will be left behind. So after you've transported the sludge, you've pumped it out of your digester and put it into the truck so you can sell it to somebody, and it's now gone to the buyer. You have to get the sludge out of the truck, let's say. And during transportation, the biomass will have made some biogas. So the first thing you want to make sure is that you relieve the gas pressure on top of the sludge, the tanker, safely, slowly and safely. And get yourself a 1.5-inch fire hose with a nice nozzle on it so you can push the sludge to the tank drain. Remember that it's not going to be making any gas anymore, so it's not going to be stirred up anymore in the tank truck, and it's going to have settled, and it's going to rat hole if you don't keep it moving, and you have to keep it moving by adding water to it. So you want to do this transfer safely, and whether you're on a truck or on a rail car, you want to make sure that you do it safely. And remember that whether it's a rail car or a tank truck, it's a confined space, so don't go sticking your head into the tank. Wear a harness on top of the tank. Tie yourself off, whether it's a tank car or a rail car. We actually had a case not too long ago where the operator, the person transferring the sludge, it wasn't the operator, it was somebody that they had hired in to do it, had not tied himself off the top of the tank car. He opened the fire hose to try and stir the sludge, and he pushed himself off the top of the tank car. So was not a good deal. Wear a harness and have a spotter there with you. Make sure you always wear the proper PPE. You have your safety glasses, gloves, hard hat, and an H2S monitor so you're not exposed to any harmful effects of H2S that may be coming off from the biogas that's going to be in the tank. So in summary, sludge, biomass, biosolids, the guys is a conglomeration of acid and methane-forming bacteria, microorganisms, and they act together to treat your wastewater. They want to convert the soluble biodegradable components into methane and carbon dioxide. There's two forms that this bacteria typically takes. It's either floccular or granular. And the final thing is that there's a market for granular biomass. So I hope you guys have some questions now, and I'm going to give it back to TJ.
Thank you, Jill, for sharing that presentation with us. We had a few questions come in during the presentation we're going to get to. I just want to remind everyone that on the right-hand side is your question panel. If you have questions for Jill, feel free to enter them in there, and we'll try to get to as many as possible before we end today's broadcast. While we're waiting for some additional questions to come in, just want to let everyone know that we're hoping to have one more continuing education webinar for our operators and managers of these systems. We're looking to have it November and December, sometime around the holidays there before the end of the year. But I just want to let everyone know in the survey, if you have some interest in a certain topic or some kind of information that you feel like you're lacking, would love to entertain that and potentially do that in one of our future broadcasts for the series. Okay, so we have some questions coming in. Our first question is when seeding a new plant or reseeding a plant, can you use municipal sludge to do that process?
Good question. There is a lot of municipal anaerobic sludge, but it's sludge that's generated from the solids digestion of primary solids and aerobic sludge generated at municipal plants, and therefore it has been exposed to sanitary sludge, which sometimes is not a good thing, and sometimes in the food and bev industry you don't want that exposure in your reactor, because you want to be able to dispose of your sludge without having been exposed to sanitary sewage. The other thing is that the sludge that you get from a municipality is flock, and it's not all just anaerobic bacteria. It's left over from the digestion of the primary solids, which could be anything that comes down the pike. Who knows what's coming down a sewage line, and it also has undigested aerobic solids in it. So it's not really that active, and it can have a lot of crap in it, like hair and pieces of bristle, pieces of rag, pieces of who knows what comes down the pike. So we don't recommend it, but definitely don't recommend it for high rate granular systems, and for lower rate CSTRs and lagoons, it's possible to use it, but again, in the food and beverage industry, we don't recommend it.
Okay, another question for you, Jill, is aside from other plants needing sludge, are there other markets that are in need of granular sludge?
I don't know of anybody that, except for other people that are starting up wastewater treatment plant, high rate plants, or people that have had trouble and need to reseed their reactor. That's the only market I know of for granular sludge. We'd love to see it. I personally think that it's a very good soil enhancer, so land apping it for fertilization is a good thing. But again, that all is doing that is based on local and state ordinances and permitting. So a lot of places don't like it, even though, like in Florida, some places in Florida, it's very hard to land app, even food and bev sludge, even though their sludge is very sandy and it would be good the sludge would be a good soil enhancer for them. It's very hard to get a land app permit in some places.
So with your comment, does that mean that you have one of the best gardens in your neighborhood?
Yes, I do, as a matter of fact. And I have, yes, put sludge on it at times. Not all the time, but if I have some left over in the lab, I will take it to my vegetable garden even and use it.
Similar to the question we talked about municipal anaerobic sludge, if they have a high rate system, a UASB or EGSB, would you still avoid using that for seed?
Oh yeah. I wouldn't use municipal flock sludge to seed an EGSB or UASB reactor at all. In fact, it won't stay in because it doesn't have this high settling velocity that the granular sludge have. And that something I forgot to say in the webinar is that obviously there wasn't granular sludge on this earth at day one. It was formed when these professors at the University of Wageningen in the Netherlands back in the 1970s were experimenting, and they noticed that in their reactors they were trying to make high rate wastewater treatment plants, anaerobic plants for food industry, again, the sugar beet industry. And they noticed that in some of their smaller scale reactors, when they were doing experimentation, that they were actually forming granules. And then they noticed how fast that they settled. And they didn't have granular sludge to start with. They only had the flock sludge. Again, they probably started with municipal sludge. But it can take like 9 months to a year to form granular sludge from flock sludge. And to keep it in the system, because in a high rate system, your upflow velocities are going to be pretty high, and the settling velocities of the flock sludge is not high like it is for the granular sludge. So oftentimes you have to keep reseeding also until you get the granule formation. So flock sludge to granules is a very time-consuming process.
And just last follow-up question about that. If a municipality has a granular-based system, would you still avoid seeding it in an industrial application? No, you could use it, but you have to be careful again that in the municipal plant, it's probably been treating, it could have been treating sanitary sewage, which means that you may have to get special permitting to dispose of your sludge if your reactor is not treating sanitary sewage. Okay. A lot of questions coming in. We're going to try to get to as many. Is there a market for floccular anaerobic sludge that you've known?
Yeah, there is at times. The problem with if you're starting up a lagoon or a CSTR, it's always good to get sludge from a non-municipal lagoon or CSTR because it will have a higher activity than it'll be higher activity biomass than you would see with a municipal sludge. The problem is that the concentration of the CSTR sludge, let's say only like 1.5 to 2.5%. So you have to do a lot of trucking, which is the expensive part of the transfer. So what we've actually done, we will actually seed lagoons and CSTRs with granular sludge, and actually we'll chew it up to make it flock, or just let it naturally turn into flock because of what it's being fed, because we can transfer a lot more kilograms of sludge in the granular form than we can in the flock form. So therefore the transportation costs would be much less.
Okay, and another question is that similar to that one is, this is from an operator in Canada, and they want to know, is there advantage of using floccular sludge over granular? And also in that same question, this person asked, is the minimum retention time of conversion from floccular to granule, was that 48 hours? I think you touched on that in a previous question.
Okay, so I'm a little confused, but I'll try to answer. First of all, it takes like 9 months to 12 months to convert enough flock sludge to go the granular sludge that you would need for a UASB system. And you would have to keep reseeding because the flock won't stay in at the higher upflow velocities seen in UASB and EGSB reactors. So that you could start, you theoretically can start a UASB or EGSB reactor with flock biomass, but you have to keep reseeding, which gets to be expensive because you need a lot of trucks, and the transportation cost is really, really high. So it's always, for me, it's better to seed with the granular sludge into high rate systems and even in lower rate systems because the transportation cost is lower. If I haven't answered your question, if that person is still on the line, if you haven't answered the question, send me an email and I'll try and answer it better.
And I guess the question would be, is outside of just seeding, is there anything in terms of operating that reactor that would promote that transfer from flock to granular?
Yes. Well, yeah, you have to have the hydraulic retention time of the influent into the digester volume has to be less than like 48 hours. And I don't know why that is. We just know that you don't get good granulation unless the hydraulic retention time is 48 hours or less. I don't know why. And again, keeping the velocities, you have to try and keep the velocities lower, and just have the right circulation. And that's the big thing. That's why I think that some of that collision coalescence, that circulation of the sludge going up, being degassed, coming back down, and it's like forming a hailstone in a thunderstorm. That you get that circulation, and that helps. But if you don't have a good settling velocity, and you don't have the granules, you don't get that good settling velocity. You don't get that circulation developing as rapidly. So, that's what you have to try to do.
Can you talk a little bit about the variability with availability with granular sludge in the North American market and how that changes so frequently?
Oh, well, this is not funny thing, but it's every year. Like right now, everybody in North America has sludge that they want to get rid of, and there's a glut of it on the market. Customers are calling us, I'd say a couple times a week saying, yeah, we have up to 30,000 gallons, 20,000 gallons, 5,000 gallons of sludge that we need to get rid of from our plant. Do you know anybody that's looking for it? Right now, nobody is looking for sludge. There's no full-scale plants coming online right now, and because all you operators are doing such a great job, everything's running well, so there's no need to reseed anybody. Now, coming this winter, I know that there's a couple of big startups going to happen, and at that time, I can guarantee you there will be no sludge available. That's just the way it works. So we're trying to hold sludge now in some reactors that we know are typically good, so we will have it to do our startups. But we have over 100. Biothane Violi has over 100 reactors in North America and Mexico, U.S. and Canada. Our competitors also have them. The granular sludge grown in any of our competitors can be used to seed our reactors and vice versa. So we try to keep track of them. And again, we try to know who has sludge so that we can have get it for you at the least cost, which means the least transportation cost.
And on top of that cost as well, we have a question about setting the price. And it sounds like there's variability in supply and demand. Can you talk about, is there a normal value per some kind of unit for sludge? And how has that changed over the course of time since the last 25 years or so that
oh my God.
these reactors have been in play?
Okay, so everybody wants to know this. And again, if you don't want to pay that much, don't charge that much. Some people want to give it away because they don't want to pay to have it taken away. And that's obviously the lower range. The upper range, I think, is about 65 to 75 cents a gallon. And we assume that gallon is at least 60,000 milligrams of VSS per liter. So we try to have pay less for less concentrated sludge because I don't want to pay for transporting water. And most customers don't. I'm saying I'm a customer. You don't want to pay for water. So, and it varies all in between there. Again, I don't set it. We try to negotiate it down as much. When there's a glut, I know that the people that want to charge 60 to 75 cents a gallon will lower their price when there's a glut, and they don't want to pay to have it disposed of, but they never go down, to nothing. So I hope that answers their question.
Thank you, Jill. Just this is more of a technical question. How, I'm reading it here, should you ever purge the biomass from a reactor? How do you know when to do it? And how do you maintain an optimal sludge bed height?
Oh, okay. That's a very good question. In the high rate anaerobic systems, you have a sludge bed height, and you want to keep the sludge bed height about at least 3 feet below the bottom of the settler at the top of the reactor. So you can hold as much sludge as you can in there as long as the bed is, about 3 feet below the top of the reactor. And you should be doing a sludge profile at least every other week. I know some of my older customers are only doing it once a month now. But we recommend once a week doing that. And you'll notice that as you get up towards the top of the reactor that, typically the concentration of the biomass decreases. I consider the sludge bed any level, the top of the sludge bed is the level with a TSS of at least 25,000 milligrams per liter or more, okay? So if you have, let's say you have 8 sludge sample ports in your reactor, the top one is 3 feet below the settler, I'm just saying. So you wouldn't want your sludge bed to grow much above level 7. Okay, and if you start to see like 10,000 milligrams per liter at 8, you would want to take some sludge out. And you can, in our O&M manuals, there's a math on how to do that. But you want to take out at least a truck at a time.
Okay.
And on the CSTRs and lagoons typically they don't remove sludge unless they take them down, and then they have to have a big sucker truck or pontoon boat come in to do that. On CSTR reactors, again, you want to maintain a certain concentration of mixed liquor suspended solids in the reactor, and you would remove sludge to maintain that mixed liquor concentration. Great.
And some leaving a little bit of the sludge discussion with some other questions here is about micronutrients. Can you talk about how important it is to add micronutrients to a reactor in terms of operating one?
Okay. Micronutrients are very important, especially in nutrient-poor wastewaters. In the food industry, unless it's a condensate we're treating, they have a lot of the micronutrients that are required by the bacteria. I always tell the story of a plant at a pulp and paper mill we did years ago in Canada, where we did a year's worth of pilot studies and fed micronutrients all the time. To make a long story short, about 6 to 9 months after they started up, the process started to go bad. They had me come up. And what finally turned out to be is that they had stopped adding micronutrients because the pump had failed, and because they were adding so little, it obviously didn't matter to them. So the bacteria didn't work well because there is no nutrient value in wood. That's why we don't eat wood. And since that means that their wastewater had no micronutrients in it. So to fix that problem, we had to give a good dose of micronutrients, and then it took about a month for it to recover. So it's important to keep those micronutrients going regularly. It doesn't mean if you miss a day that it's going to be bad. It takes like 6 to 8 weeks before you see a problem. if you don't feed them micronutrients. But it's best just to take them like a daily vitamin and have them work well. They're really important to the, to keep the bacteria healthy.
Okay, we're winding down our questions. We have one more here, I think, and it is related to, the question is what is the long-term fate of polymer used to flocculate sludge? Can you comment on that, Jill?
It depends on the type of polymer. There's a Brazilian different types of polymer out there. So its fate is totally dependent on its what its makeup is. A lot of them are biodegradable actually, so that they'll be broken down in the system eventually and will be turned into biogas. And you have to be really careful with polymers in these anaerobic systems, even in solids digesters, because a lot of the in municipal plants, they will use polymer to thicken their aerobic sludge before they put them into an anaerobic digester for further reduction. And those polymers can actually be inhibitory to the anaerobic biomass. So you have to be really careful about what you're using. You don't want to use non-biodegradable, GRAS, they're called, generally regarded as safe polymers, so that they are digestible.
Okay, well that wraps up for today's presentation and all the questions as well. If there's a question that you need more clarification on, Jill's contact information is on the screen there. Feel free to follow up with her or myself. Again, I'd like to thank everyone for taking some time. You are a very important part of our business, and supporting you is really important to us. And if you have future topics, again, fill them out in the survey. We'd love to hear what your opinions are and how we could improve this educational event. And we look forward to hosting you again, either in late November, early December, for our final webinar for this year. So this concludes our presentation. Thank you again, and wish everyone a good rest of your week.